Okay, let's go for the next chapter. Chapter 22 is gonna be Gauss's law. Okay, I will use Gauss's law to calculate the electric field for some continuous distributions, while in solids, correct? We know another technique, which is the Coulomb's law. Great. Now to do that, let's go with the electric flux. Let's take the electric fields to be like a flow, right? Something that flows. Perfect. Then let's represent the electric field correct in this direction. This is the electric field. Imagine that we use a funnel, right? A funnel, correct, to catch the electric field. Now this flux then is proportional to the area of this funnel, right? This is the area. If we increase the area, we increase the amount of flux, right, going through. Also, if we increase the intensity, the intensity of the electric field, of course, the electric flux increases too. Now, what happens if we rotate the funnel? Imagine this is the funnel right here. We rotate it in that way. Well, in that case, we have zero electric field going through. Means that also the electric flux is proportional to the angle, right? Right here we have maximum, right here we have zero. The function that gives us that when, imagine this is the direction of the funnel, correct? When the field is parallel to this area, let's say, this is the direction of the area, so we have maximum, which is perpendicular, correct? Perpendicular is gonna be zero. The function is cosine, right? So it's proportional to cosine theta. Now let's combine out of these three factors. And what do we have? The electric field is proportional to area electric field, right, times cosine theta. To eliminate this symbol, we need a constant. The constant is used mainly to find the unit, to match the unit. It's found that K, the constant of proportionality, is 1. So then we get that the electric flux is equals to A, the area, right, electric field, cosine theta. Correct? Perfect. Now, let's go back to this formula, which is this one right here. Every time, remember, every time we have a vector like the electric field and cosine, or a vector and sine, we can relate these two quantities to cross product or the dot product. Like in this case, right? We can represent this AE cosine theta as the dot product, right, of A vector times E vector. Correct? Remember, this is equals to A, E, right, cosine theta. Means that we can represent this area also as a vector, right? Now imagine this is the surface and this is the vector, the direction. This is the magnitude, this is magnitude, and this is direction, correct? And this is the vector A, the area vector A. So this area vector A, area as a vector, is equals to the magnitude times the direction, which is perpendicular to the surface of this opening, let's say, the surface. Perfect. Now, taking this into account, we can represent then the electric flux to be equals to this dot product, right? Now we have these two vectors, and the area now is a vector. It has magnitude, it has direction. Perfect. Now, let's go to the case when we have a infinitesimal changes, correct? We can use this also, use integrals when we have surfaces, more surfaces, correct? So we can represent this also in this way. It's equals to the integral of the electric field, correct, that the A. Right? we represent this condition in this way too. Correct? This is a case mainly when the electric field is not constant, but it changes. It changes where we can use this equation. Perfect. So we have again that the electric field is equal to the integral. Right? Okay, it's a vector, right? Vector. Correct, vector. Okay. dA. We use the dot product. Perfect. Now, what happens when we're dealing with a closed surface? Imagine that we have this closed surface like this, right? And we have an electric field that is not constant, correct? And goes to this closed surface. Well, it says closed surface, correct? Now let's see what happens is the electric field right here, electric field. Imagine that we are right here on this area, right? So this is the area as a vector dA, right, for example. They simply happen right here, right? This is, again, this is perpendicular. This is the element of area, correct, to find the magnetic flux, the electric flux, correct? Perfect. Now, by convention, we take this condition when the electric flux leaves the surface, the electric flux is positive, right? Well, when we're dealing with closed surface, of course. When the electric flux is entering the closed surface, right, the electric flux is gonna be negative by convention, correct? Perfect. Now, well, we have this case, and what should be the in this case, the total magnetic flux through this surface, closed surface, is gonna be 0. Because the same amount entering, the same amount is leaving the closed surface. So the electric flux then is gonna be 0 for a closed surface. Perfect. And we have more surfaces like this one. Imagine we have another one like this, correct? So we have the electric flux going in this direction, the same thing, right? The electric flux to this surface, closed surface, is gonna be 0. Also, we can have, right, this picture like this, right, like that, and we get the same answer, correct? Perfect. Now let's go to the Gauss law. This is again working only with the electric flux. Now let's see how we relate this electric flux to the charges. That is actually the Gauss's law. Let's do it. Oops. Okay, let's see. Let's go back to the point charge, positive point charge, right? Remember, we have electric field. The electric field is going out right from the positive charge, correct? Now let's try to create a surface, a closed surface. These surfaces are called the Gaussian surfaces. We have especially 3 types of Gaussian surfaces. We have the cube, we have the sphere, and we have the cylinder. And we have the cylinder. These are the main Gaussian surfaces that we use in calculating the electric field when we have a charge distribution. Okay, perfect. Now, for this case, depends on the symmetry, right? So let's use this sphere to be, remember this is the electric field, to be the Gaussian surface, right? Gaussian surface. Perfect. Now let's try to calculate the electric flux, right, going through this surface. What is the equation for the electric flux? Well, it's gonna be this one right here, right? It's gonna be the electric flux is equals to the integral. When we're dealing with closed surface, we use this notation, right, on the integral, right, times E dot dA. And this is equals to the integral of E, correct? Well, E, which the eraser right here, correct? E, right, the A. Because look, we have this area right here. Let's take any area, element area is parallel, right, to the electric field. When we're dealing with the dot product, one more time, is gonna be A equals sine theta. But what is the angle between that area, right, or the normal of the surface, right, times the electric field, right? They are parallel, so the angle is 0, cosine 0 is 1. Okay, great. And then this is equals to, where we're right here, E, right, times the integral of this surface, correct? And what is that? Well, this is the electric flux equals to E, correct, times the area. What is the area of the sphere? 4 pi r squared, correct? But when we are dealing with point charges, we know that the electric field for a point charge is equals to kq over r squared, correct? So then this is equals to kq, correct? kq over r squared times 4 pi r squared. But what is the value for k? Well, the value for k, remember, another value is gonna be, okay, the electric flux is equals to k over 4 pi, right, epsilon naught, correct, r squared times 4 pi r squared, correct? And what should be then the electric flux? The electric flux in this case is equals to from here, is equals to just the charge divided by epsilon naught. Correct? So we found these equations for, this is for a charge, in this case is the positive charge, correct? The total flux created, electric flux created by this positive charge is just equals to the charge, right, divided by epsilon naught. Perfect. Now, when we relate this equation, right, with this one, we create the Gauss's law. And that's gonna be Gauss's law. Okay, let's do it. So we have Gauss's law. So when we combine these two, we create that this electric flux is equals to this cross area, right, of this dot product, and it's equals to the charge divided by epsilon naught. This is again the Gauss's law. Or in general, this is when we have, remember we found this when we have only one charge, positive charge. What happens if we have a bunch of charges? Well, in that case, this charge is going to be the total charge, the charge enclosed by this Gaussian surface. So in general, we have, that's going to be, right, the total charge enclosed by a Gaussian surface, correct? Right, and we're representing this in this way the Gauss's law. This equals to integral of this product, and it's equals to, right, the total charge enclosed by the Gaussian surface divided by epsilon naught. That's the again Gauss's law. Got it? Okay. Now let's apply this law to some cases, some distributions, and let's try to find the electric field. For example, let's do a spherical shell, right? A spherical shell, which is charged, right? And is uniformly charged, okay? Uniformly charged. Perfect. Now let's try to find the electric field inside and outside. Okay, let's go outside. Right side. The technique is, remember, using a Gaussian surface. Imagine that's the Gaussian surface, correct? And then let's use the equation. right here for this closed Gaussian surface, correct? We have this product. We know because this is a sphere, this is a sphere, we can just go to the magnitude, right? The A right here, the A is equals to the total charge enclosed, right? The total charge enclosed divided by epsilon naught. Correct? Because it's constant around this surface, so we have the electric field. What is the area? Should be 4 pi, the area of the sphere, 4/3 right part r square. That's the area of the sphere? No, that's not it. That's for the volume, right? It's 4 pi. Perfect. 4 pi r square equals to charge over epsilon naught. Correct? From here we can find that outside the electric field is equals to the charge over 4 pi r square epsilon naught. Correct? Which is the same as a point charge. Right? This is telling us that actually this charge behaves as if all this charge is concentrated at the center, because that's the formula for a point charge, right? The electric field of a point charge. So this behaves, of course, it's when you are far away, right? That all the charge is concentrated at the center. Perfect. Now, what about inside? For inside case, we use the same technique. We create a Gaussian surface inside. But when we apply this equation again, we have that this integral times the area is equals to the total charge enclosed right divided by epsilon naught. But what is the charge enclosed by this Gaussian surface? It's zero. There's no charge. The charge is outside, right? Because it's a shell, a spherical shell. So the charge is outside, right? And because of that, the electric field inside is gonna be zero. Correct? Perfect. Now let's see. Let's make a graph that represents, right, the behavior of the electric field inside and outside. Great. So inside we found that is zero. So let's represent then. Okay, this will be the distance r, and this is the imagine through the center. It's through the center. Imagine it goes through the center. Correct. It's the center right here. Correct. Like this. Perfect. So this is the electric field. So this is the h of the sphere. Correct. Imagine this right here is the quantity of the electric field. This quantity q over right 4 pi right r squared epsilon naught. Okay. In this inside we know that this is zero, right? This is zero electric field. But when it goes to this h, correct, we jump to this amount, right, and then decreases inversely proportional to r squared. Correct? And that's gonna be the graph for this shell. Now, imagine that we have a solid sphere. It's a non-conductor, and we have a distribution of charges inside, and the density is constant. Perfect. Now let's see what happens when we have that volume. When we have that volume. Again, we have this volume, the volume with radius r, correct? And this is a non-conducting sphere, means that all the charges stay in the same position all the time, correct? It's a non-conductor, right? And also well, the density is constant. Okay, the same thing. Let's find the electric field outside and the electric field inside. So to that, remember we use the Gauss's law, right? Let's do it. Let's create this Gaussian surface right outside, and this is similar to the previous example, right? The electric field is gonna be equals to charge over 4 pi epsilon naught times r squared. Okay, the same thing. Now, what about inside? Inside, Inside, imagine that we have this surface, right, or this volume with radius r. Because the density is constant, right? How do we define the density in general? Density for the charge in this case is gonna be the total charge divided by the total volume. But this is the volume for the total sphere, the complete sphere. From here, what do we have? Well, from here we can say, well, that's gonna be the density. Perfect. Now, what about we were looking for the electric field again inside? Well, we use the integral one more time. What is the integral? Right here. Well, this is the integral, right? It's gonna be what? The integral of the closed surface of this quantity, correct, must be equals to the charge enclosed, correct, divided by epsilon naught. Now, how we can find the charge enclosed? How we can find this charge? Well, the charge enclosed is equals to the charge enclosed is gonna be equals to density, right? Density times volume, right? With that radius, correct? Volume with that radius. Now let's substitute again. This is the total charge, right? This is the amount of charge that is enclosed by this surface. Now let's substitute this value right here. And what do we have? The density. So equals to the total charge, correct, times the volume of with that radius, correct, divided by volume of the total sphere, correct. And what is this? This is equals to the total charge. What is the volume? It's gonna be 4 pi r, or 3 pi r cubed, right, divided by the total volume, which is 4 pi or 3 pi, correct, r cubed. In this case, what do we have? Well, we have that this is equals to just the total charge times r cubed over big R cubed. Correct? Perfect. That's the total charge right here. So, or the charge enclosed. Now let's continue then. What do we have? Let me do it right here. Let's go to this. What's gonna be the electric field times the area. What is the area of the sphere? One more time. 4 pi r squared, correct? Must be equals now to this total charge times r cubed over right epsilon naught r cubed, big R cubed, correct? Now from here, what do we have? That the electric field is gonna be equals to this charge times r divided by 4 pi epsilon naught r big R cubed, right? And that's the electric field inside of this solid sphere, correct? Now let's see what happens at the edge, right, at the surface right here. At this surface, this r is equals to the radius. And what do we have? Well, it behaves as a we have the equation, the formula for a point charge, right? Which is the charge equals to, not the point charge, but now taking the radius of the sphere, right? Equals to charge 4 pi, right, epsilon naught times r squared, which is gonna be similar, right, to the general equation, which is this one for electric field of a point charge, correct? Perfect. Now let's see how the graph looks like, how the electric field behaves. As you can see, look, this formula gives us the charge is constant, these are constant, also radius is constant, so it means actually that the electric field is equals to a constant, let's call that constant C, any constant times R, right? So it looks like it's like a, this is the equation of what? Of a linear function, correct? So we have a linear equation right here, inside. So what do we have then inside? Well, one more time, it's at the center, correct? So inside is linear, in this way increases, correct? The electric field later at the H, this is H right here, imagine, okay? We have this formula, correct, which is what? Q over 4 pi, correct? 4 pi what? 4 pi epsilon naught, 4 pi epsilon naught times what? Times r square, correct? Times r square. Perfect. And what happens after that? Well, it behaves what with this r and decays in that way, or decreases in that way. Correct? And it's gonna be the graph for this solid sphere. Okay, perfect. Let's go for the last example using Gauss's law. That's gonna be an infinite sheet, right, which is charged. Okay, let's do it. Let's do it. The last example. We have this infinite sheet of chart, right? Imagine this is the surface right here, correct? This is positively charged, okay, correct. And in this case, we use as the Gaussian surface, right? This cylinder right here, correct? Imagine that cylinder. Imagine, okay. We have again the electric field again perpendicular to this surface, right? Gonna be in this direction, right? And the same thing as the surface, right? It's in this direction. This is the electric field, and this is the area as a vector, correct? The same thing happening on the other side, right? We have the electric field, and also we have the area, correct? The electric field, and we have the area. Also, we have another area, right? In this direction, this is the area, and now we have the electric field in that direction. Correct. Now let's find the electric field again using the same equation. Okay, let's do it. So then the integral, right, for this quantity. Well, in this case, we can see that this is equals to this product, right? But you can see this surface, these two surfaces are related to the flux, right? We have flux going up and flux going down, but no, we don't have flux going to the side. So in this case, it's gonna be equals to, let's call this case 1, or surface 1, and this is surface 2. So then the total as the product right here is gonna be E1 A1 plus right E2 A2. Correct? But according to the Gauss's law, this equals to what? It must be equals to the charge, right, enclosed divided by epsilon naught. In this picture, it's better to use density. It's better to use the surface density, which is equals to charge divided by epsilon naught. No, divided by area, not epsilon naught. Divided by the area. Divided by the area. From here, right, the total charge or the charge enclosed by this Gaussian surface is gonna be equals to what? It's gonna be equals to sigma times the area. Correct? And then what do we have? Well, we have that this product times plus this product, right? In this case 2 must be equals to sigma times area over epsilon naught. But these two areas are the same, right? Area 1 is equals to area 2. Oh, so we expect, right, to have the same electric field. So what do we have then at the end? 2 times the electric field times the area is equals to sigma area over epsilon naught. And finally, what do we have? We have that the electric field produced by this huge plate or flat sheet, right, equals to sigma divided by twice epsilon naught. Correct? So what do we have then? Oh, we can represent also this in this way. Look in this way. We can represent this in this way. We have this huge plate. Mine is possibly charged, right? So we have the electric field, right, in both directions. And the electric field is equals to sigma divided by 2 epsilon naught. Correct? Also, we can have, we did this in the last chapter, right? Another plate, but now is opposite in charge. They have the same density, surface density. Well, in this case, remember this is the direction for the electric field, and the same thing this is the electric field is equals to sigma over 2 epsilon naught. What happens when we combine these two? What do we have? Well, we have this important result that we use in capacitors, correct? What is the electric field between these two capacitors? Well, it's found to be equals to sigma over epsilon naught. Correct? The same result that we found using Coulomb's law is found using the Gauss's law. Correct? Perfect. And with this, we finish the chapter. It's a short chapter, and see you in chapter 23. Okay.